This is a continuation of the previous video. In this one, we'll talk in a little bit more detail as to how to prove this limit statement. So this is the statement written out in symbols. And so in the proof, after beginning by saying let epsilon be a positive real number, your task is to figure out how to choose this number delta. So how should you do that? Well, the first step is to combine the 75 and the 2, and then to factor this. Just a word about the factorization of that. Since we know that the limit of this thing is really 75, it follows that when you plug x equal to 7 into this, it has to turn out to be 0. And that means that x minus 7 has to be one of the factors in the factorization. Now once you know that x minus 7 is a factor, since the product has to be 3x squared, this has to be a 3x, and then you just have to figure out what it takes to get this minus 77, so it has to be plus 11, and then you should just simply verify that the cross term, the 10x term, works out. That's minus 21 plus 11, which is really minus 10. Okay, so the fact that you know that one of the factors has to be x minus 7 makes this factorization really very simple to get. Now we know that one of our assumptions in the proof will be that absolute x minus 7 is smaller than delta, and therefore after writing this down we know that this is smaller than delta, and so we get that this thing is smaller than delta times 3x plus 11. Now we know that ultimately we want to be able to make this thing smaller than epsilon, and so a number of you in the class would have done something like the following. You would have said choose your delta so that delta is equal to epsilon over 3x plus 11, and if that were the case, then this would automatically be smaller than epsilon and you would be finished. Unfortunately, that doesn't work. So my question to you is, why does this make absolutely no sense at all? Well, at the moment in time when you're to be choosing your delta, all that you really have at your disposal is the epsilon that was given to you in the very first step. The x isn't going to show up until after you choose your delta. The x shows up in the third step. So by telling me the delta equals this, the reader looks at that and says, well, what is that number? I don't have any idea what this x is because there isn't one. So this is not a concrete choice of a delta, and therefore this can't work. Well, you may then say something like, how about if you ask for delta to equal this for some real number x? Would that work? And again, that can't work either, because if it's equal to this for some specific x, at the very next step, somebody's going to give you a real number, and what if it's different from the x that you happen to use in your second step? Well, if it's different from that, then you won't be able to prove this statement. In fact, you'll be proving this statement with this for every changed to a there exist, which is a considerably weaker statement. Okay, so there's no way around it. There's no possible choice of this delta that has any kind of an x in it at all at this stage. The delta that you pick is going to have to work simultaneously for every single x satisfying this condition. Okay, so we come back to the question, how are we going to choose that delta? So let's pick things up from this statement here, which we had on the previous page, that this quantity is smaller than delta times 3x plus 11. So basically what you need to do is you need to get an upper bound on this absolute 3x plus 11. Because if I could replace that by a single number without any x's in it, I wouldn't have any trouble figuring out how to make that smaller than my epsilon. Now notice that whichever delta we eventually wind up choosing, any smaller positive number would work just as well, and so there's no loss in generality in assuming that delta is smaller than 1. I could use 1 or any other number. It doesn't matter which number I pick, any positive number. So just to be concrete, I'll use delta smaller than 1, and you'll see that we'll make use of that in the next step. Now the main tool that you get to use in getting an upper bound on this 3x plus 11 is the triangle inequality, which says that if you take the absolute value of the sum of any two real numbers, it's less than or equal to the sum of the absolute values. So to get our upper bound on absolute 3x plus 11, what I do is wherever I see an x, I add and subtract a 7, I copy everything out, and then I group the x minus 7 with the 3, and I simplify the rest. 21 plus 11 is 32, so this is actually equal to this. Now I apply triangle inequality, where this is my a, and this is my b. So that's smaller than 3 times absolute x minus 7 plus absolute 32, which is just 32. But absolute x minus 7 is smaller than delta, and delta we've chosen to be smaller than 1. So that's smaller than 3 times delta, which is smaller than 3 times 1 plus 32, which is 35. So that gives us the upper bound that we wanted on absolute 3x plus 11. So now to make use of that upper bound on absolute 3x plus 11, we look back here. Okay, we know that this part is smaller than 35. That's what we just got in the previous step. So this whole thing is smaller than 35 delta, which is what we wanted. So that gives us this step here. This thing is smaller than 35 delta. But our overall goal was to make this thing smaller than epsilon, and we will succeed in that if we just simply ask for this thing to be smaller than epsilon, smaller than or equal to epsilon. And so this is another condition that we want to impose on our delta. So now we've got two conditions. We've got this one, and we've got this one. The easiest way to satisfy this condition and also this condition, and also to make sure that we get a positive real number out of it, we just take delta to be the minimum of those two numbers. So that tells us how to handle this step in the proof. We just simply choose our delta to be this. And of course it took quite a bit of work to do that, but that's the result. And now we're ready to go back and actually write up the proof. So put your video on pause and see if you can write the proof, now that you know what to do when you get to this step, and see if you can't make all of the other steps work. And when you come back, you can compare your solution to mine. Here's my proof. At the first step, you should say let epsilon be a given positive real number, then choose delta to be that number that we came up with on the previous page. Then we say let x be a real number, and then we say suppose absolute x minus 7 is smaller than delta. And next, we have to prove that this inequality can be deduced. And the way I do it is I start on the left side, see, then start on the left side, and then through a string of inequalities, all going in the same direction, I write down things, each of which I know to be true, finally terminating in the fact that it's smaller than epsilon. And the fact that we had a single strict inequality will mean that this is strictly smaller than epsilon. The benefit of writing it in a display rather than in line is that when it comes time for me to give a reason for one of my steps, I can do so with this little parenthetical comment. Okay, so let's look at it. This is equal to this just simply by factorization. This is smaller than this because that factor is smaller than delta, and I wrote the reason there. And now I'm doing a little calculation to get my upper bound on this. Okay, so that's equal to, I added and subtracted 7, that's equal to this. And now I'm ready to apply my triangle inequality. It's less than or equal to delta times absolute value of this plus absolute value of this, and that's what I wrote here. And that's smaller than 35 delta because this is smaller than delta, which is in turn smaller than 1 from here. So this smaller than 1 So this is smaller than 3 plus 32, which is 35 delta. And 35 delta is in turn smaller than epsilon because of our assumption that, of this assumption here, which causes delta to be smaller than epsilon over 35. This completes the proof. And so we're done.